previous part, we understood what was tricolorability, and I'll just quickly review that definition right now. So first, to understand tricolorability, we understood what is a strand. A strand, simply speaking, is the stroke of your pen a stroke of the pen that you can make without lifting your pen. So like in the trefoil knot, we have 3 strands, right? And then the point of tricolorability is that we can somehow color each strand a different color. We need exactly 3 colors. Color each strand a different color in any way you want, such that at each crossing, so we say at each crossing there are 3 strand pieces meeting. Each of them should either all be the same color or should all be different colors. So either you should have RGB on all of them, or you should have just either RRR, GGG, BBB. Like that, if you can color this in some way, whatever way you want, then this knot is considered tricolorable. If you could not do that, it's not tricolorable. Now we will prove that if a certain projection of a knot is tricolorable, then any transformation of it using Reidemeister moves and planar isotopies is also tricolorable. So let's just quickly go through that proof. So by Reidemeister's theorem, we just have to consider the 3 Reidemeister moves. And if we can prove that given a tricolorable part and then do a Reidemeister move, and if it's still tricolorable, we can show that tricolorability is invariant under Reidemeister moves. So let's consider R1. So let's just say you have a, green strand like this. Now, by Reidemeister theorem, by Reidemeister move 1, this can be taken to Now we see that all 3 colors meeting here are the same, so this is still tricolorable. The whole knot outside here was tricolorable. This crossing still works, so now we have that this knot also here is also tricolorable. So thus, for Reidemeister 1, if the previous thing is tricolorable, do Reidemeister 1, it's still tricolorable. So that was fairly easy. Let's do Reidemeister 2 now. Let's just say, for example, there's many cases we have to check. I will just show one, as always, and you can check all the cases on your own. Because generally in these Reidemeister move sort of problems, there's a lot of cases to check. I will just show one case for now. So I'll just take the case of, let's say, some random color, say red, green, sorry, and blue. Now, Reidemeister move 2 says you can just shove, let's say, a piece over or something, right? So I'll just consider that, say you shove it over. However, now at these 2 crossings we have a problem. We have 1 green and 2 blue meeting. 1 green meeting right here and 2 blue meeting. This is not okay for definition of tricolorability. So now you must do something to fix this. Well, we can do whatever we want with these strands. The only condition is that we cannot change these ones because the whole rest of the knot is dependent on these strands. We want the rest, because the whole rest of the tricoloring is dependent on the fact that this is green, this is blue. So the only one we can change is this one. So let's try changing that. let's say you change it to a red. Well, now that fixes the problem. Red, green, blue, this is tricolorable. So now we have proven, at least for one case, that Reidemeister 2 is tricolorability is invariant under Reidemeister 2. Now finally to Reidemeister 3. And as always, Reidemeister 3 involves a lot of cases and is usually very messy. I'll just show one case, and the other cases are similar derivations. So let's look at one case of Reidemeister 3. Okay, let's look. So I'll consider the following case. So this is one starting position, and this is clearly tricolorable. Hold on, there's a mistake. This should be green. This we see is clearly tricolorable. This point we have RGB. This point we have BBB, which is also fine. And this point we have RGB. So we start as a tricolorable. Now let's imagine pushing this strand over. Let's see what we get. It's important to note that this must remain green, the endpoint here must remain green, the endpoint here must remain green, the endpoint here must remain red, the endpoint here must remain blue. That's important to remember while doing this. So I'll just show you the solution. Just basically we do this. We do this. And we do that. So as you can see, the strand is still blue, as it should have been. The endpoints of these did not change. And we had green, green, blue, blue, red, red, green, green. And I changed the internal structure so that it remains tricolorable. This point is RGB, RGB, RGB. So thus in this case of Reidemeister 3, we found that tricolorability is conserved. And we can check all the other cases, and we can find that tricolorability will be conserved in those cases. So thus, even a projection of a knot, and let's say it's tricolorable, we keep changing it. If we keep changing it, the other projections are also tricolorable. We just showed that. Now in the next lecture, we will see how we can apply this to show that some certain knots are different, and then we will also continue, and we will also introduce a new topic which is called rational tangles. So see you in the next lecture.